Welcome back to AI.Code.Cast, everyone. Ready for another deep dive?
Always excited to dive in.
Great. Today, we're going to be tackling a classic coding challenge.
Ooh, a classic. Always fun.
You know, the kind that pops up in technical interviews all the time?
Mm.
Merging two sorted linked lists.
Yes, merging sorted linked lists.
It's like you have two lines of folks.
Okay, two lines of folks. I'm picturing this.
Each line is lined up from shortest to tallest.
Shortest to tallest. Got it.
And we got to combine them into one line.
Right. Combine them.
But we have to maintain that height order. So the shortest people are still the front and the tallest are at the back. No disrupting the order within the original lines.
Right. Can't just shuffle them randomly. Got to keep it sorted. So, two sorted lists, merge them into one, still sorted. That's our challenge.
Exactly. You've got these two lists already beautifully sorted in ascending order. And your mission is to weave them together into one new list that's still perfectly sorted. Why is this problem such a brain teaser for so many people?
Well, first off, linked lists can be tough to picture in your head. They're not like arrays where everything's neatly lined up.
Right, they're all over the place.
Plus, you're working with pointers. And those are like those finicky little arrows, you know?
Oh, yeah.
One wrong move and whoosh, your whole list can get jumbled up.
You could end up with a cycle in your list.
Oh, yeah. A loop. Not good.
Or even worse, lose a node completely. Coiners, gotta be careful with them.
Before we dive into all the elegant solutions, I'm curious, how would you approach this? Like, if efficiency wasn't the main concern, what would be your first instinct?
Well, if I didn't have to worry about being super efficient, I'd probably just start with a brand new empty list.
Okay, a fresh start. I like it.
And then I just walk through both of those input lists, comparing elements one by one.
So like taking the smaller person from each line and putting them into our new line. Yeah, exactly. Like, okay, this person is shorter, they go first. And then just keep doing that, going back and forth between the two lists, picking the smaller element each time until you've gone through all of them. And there you have it, your merged list.
Sounds simple enough, but this is a classic coding interview question.
Yeah.
So I'm guessing there's a catch.
Of course there's a catch. The problem with that approach is that it's not very efficient. You end up doing way more comparisons than you actually need to.
Yeah, you're not really using the fact that the original lists are already sorted, are you?
Exactly. You're treating them like they're just random lists, when really there's a smarter way to do it.
That's like you're sorting things that are already sorted. So let's get into some of those smarter approaches. I hear there's this really elegant recursive solution. What's the secret sauce behind that?
Recursion. It's all about breaking a big problem down into smaller, self-similar problems. You know, like those Russian nesting dolls.
Love those.
You open one up and there's a smaller one inside and another one inside that and so on.
So how do we apply that nesting doll idea to our merging problem?
Okay, imagine you have two stacks of cards and they're both sorted from, say, lowest to highest.
Okay, I'm with you. Two stacks of sorted cards.
You compare the top cards from each stack. Whichever one is smaller, that's the winner. That becomes the top card of our new merged stack.
Gotcha.
And then you recursively do the same thing with the rest of the cards.
So it's like we're saying, all right, we handled the first card. Now you, smaller versions of ourselves, take care of the rest.
Precisely. It's like delegating the work. And eventually you'll hit this base case. Like one of the stacks is empty. There's nothing left to compare.
Oh, I see. So we just return the other stack.
Exactly. And that makes sure our recursion doesn't go on forever. Otherwise, it'd be like those nesting dolls, never ending.
Okay, this recursion thing is kind of blowing my mind a little. So let me see if I've got this straight. We compare the heads of our two lists. The smaller one gets added to our new list. And then we call the function again. But this time with the rest of that list and the other list.
You got it. It's like a little dance, back and forth, comparing, adding, calling the function again, until all the elements are beautifully merged. Super elegant.
Right. It is elegant. But I'm thinking, wouldn't this get a bit crazy with memory if our lists were huge? All those recursive calls adding up?
You're right to be thinking about that. Recursion can definitely be a memory hog.
Because each call adds a frame to the call stack.
Yeah, exactly. And if your lists are massive, you might run into something called a stack overflow.
Oh no, stack overflow.
Your program basically runs out of memory, so as cool as recursion is, sometimes it's not the most practical choice.
So I'm guessing that's where iteration comes in.
You got it. Often iteration gives you better space efficiency, especially for those really big lists. But it might involve a bit more juggling with those pointers.
Pointer juggling. Sounds like we're in for a fun ride. We'll dive into that right after this.
Okay, so we're back and ready to tackle this iterative approach to merging our sorted linked lists. You mentioned pointer juggling before the break, and I have to admit that sounds a little intimidating. I get it, pointers can be tricky, but with a good strategy, it's all very manageable. So with the iterative approach, we basically walk through both of our lists at the same time.
Okay, so we're looking at both lists simultaneously.
Exactly. And as we're walking along, we compare the values at the heads of each list.
So, like, which list has a smaller value at the beginning?
Yeah, and whichever one is smaller, we add that value to our new merge list. And then we move on to the next node in that list.
Oh, I see. So it's kind of like we have these two runners, one for each list, and we're always checking to see who's ahead in the race to the smallest value.
That's a great way to think about it. And now, here's a handy trick to simplify this whole process. We can use a dummy node.
A dummy node. I don't think I've come across that before.
Well, think of it like a placeholder at the very beginning of our merge list. It's kind of like a temporary starting point, you know?
Oh, okay, I get it. So we don't have to worry about all those weird edge cases right away.
Exactly. It just makes things a lot cleaner and easier to manage.
So it's like we're giving our runners a designated starting line even before the actual race begins. I like it. But how do we actually use this dummy node when we're merging?
All right, so first we create our dummy node. Easy peasy. Then we need another pointer. Let's just call it current.
Okay, current. We've got a dummy node and we've got current.
And at the beginning, current is pointing to our dummy node. This little current pointer is going to be our workhorse, building our merged list brick by brick.
So current is like the construction worker carefully putting the pieces together.
Precisely. Now, we look at the values at the heads of our two original lists. Let's say list 1 has a smaller value at the head.
So our runner from list 1 is currently winning the race.
Exactly. So current steps in and says, all right, list 1, you're in the lead. I'm going to attach your head node to my next.
So the head of list 1 becomes the second node in our merged list right after our dummy node.
Exactly. And then both current, our construction worker, and the pointer for list 1 move one step forward.
Oh, I see. So current is now pointing at that newly added node from list 1, and list 1 is ready to compare its next node.
You got it. And we just keep repeating this process, comparing, attaching, and advancing, always adding the node with the smaller value to our merged list.
Okay, I'm following along. But what happens when one of the lists runs out of nodes? Like one of the runners hits the finish line?
That's a great question, and this is where things get really interesting. Remember, our original lists were sorted.
Right, that was the whole point.
So if one list runs out of nodes, that means all the nodes left in the other list have to be bigger than everything we've already merged.
Because we were always picking the smaller value, right?
Exactly. So if one list is empty, we can just attach the rest of the other list directly to our merged list. We know they're all going to be bigger anyway.
It's like the remaining runner gets to just sprint to the finish line.
Exactly. And then, last but not least, we go back to our trusty dummy node.
Ah, yes, our placeholder.
We simply return dummy.next, which basically skips over that placeholder and gives us the actual starting point of our merged list.
Okay, I think I'm getting the hang of this iterative approach, and it seems pretty efficient, right? We only go through each list once.
You're absolutely right. It's very efficient. But I'm curious to hear your thoughts on space complexity. Are we creating a lot of new nodes with this approach?
That's a great question. I'm thinking, with the dummy node, we're only adding one extra node, right? And then we're just rearranging pointers, not really creating a bunch of new nodes.
You nailed it. The beauty of this iterative approach with the dummy node is that it uses constant extra space.
So no matter how gigantic our lists are, we're not using up a ton of extra memory.
Exactly. That makes it a really powerful solution in many scenarios. Now, since I know you love pushing the boundaries of efficiency, I have a question for you. Could we make this iterative approach even more efficient? Like, could we ditch the dummy node entirely?
Oh, wow. That's a great challenge. Ditching the dummy node. I'm intrigued. But how would we even begin to do that?
Well, instead of that placeholder, we'd have to figure out who's going to be at the very front of our merged list right from the get-go, just by looking at the original lists. And then it's all about carefully managing those pointers to make sure everything gets connected in the right order.
Sounds like some serious pointer gymnastics. I'm up for the challenge. Let's explore that after a quick message from our sponsors.
And we're back, ready to do some serious pointer manipulation, no dummy nodes this time.
That's right. We're going for it. So remember those two lines of people?
Yep, our shortest to tallest lines.
This time, no placeholder person in front. We're going to figure out right away who's leading the pack in our merged line.
Just by looking at who's the shortest in each of the original lines.
Exactly. So let's say the shortest person is in line 1.
Okay, so the head of list 1, that's the starting point of our merged list.
Got it. Now, we need a couple of pointers to keep track of where we are in each list as we're going along.
Okay, one pointer for list 1 and one for list 2. Like 2 fingers, gracing our way through the lists. And here's the trick. We're going to use another pointer. Let's call it Prev.
Okay, Prev. What's Prev doing?
Prev is going to keep track of the node that comes before the current one in our merged list. It's key for smoothly inserting nodes from list 2.
So Prev is kind of like our safety net,
Yeah.
making sure we don't accidentally disconnect any parts of the list as we're inserting.
You got it. So let's say we're comparing values, and the person in line 2 is shorter than the one in line 1.
Okay, so list 2 has the smaller value.
We want to insert that person from line 2 into our merged line right after Prev.
It's like we need to carefully unlink the chain after Prev, slip that person from line 2 in there, and then reconnect the chain smoothly.
Okay, first, we make Prev.next point to the node from list 2. This inserts list 2's node right where we want it after Prev.
Okay, got it. List 2's node is in the right spot. But what about the node that was originally after Prev? We don't want to lose that one.
Absolutely. We got to make sure that node doesn't get lost. So we take the node from list 2, and we make its next pointer point to the node that was originally after Prev. It's like a little swap.
A pointer switcheroo. Okay, so we've rerouted the connections to make space for the node from list 2, and we haven't broken the chain. Nice.
And then we just move Prev and the list 2 pointer one step forward to get ready for the next comparison.
So we keep doing this, comparing, inserting, advancing, until one of the lines runs out of people.
And then, just like before, we can attach the rest of the other line to our merged line.
I'm really starting to see the similarities between this in-place approach and the dummy node approach.
They're very similar, but here we're getting rid of that extra dummy node and manipulating the original lists directly. It's a great way to get really comfortable working with pointers.
It definitely feels like we've leveled up. So in terms of efficiency, what's the time complexity here?
It's still O of m plus n because we're looking at each node in both lists once.
Okay, same as the other approaches. What about space complexity? Is this better than recursion?
You bet. With this in-place iterative approach, our space complexity is O of 1. We're only using a fixed amount of extra space just for those pointers.
Wow, so no matter how massive our lists are, we're only using a tiny bit of extra memory.
Exactly. That's the power of this approach.
Well, we've certainly covered a lot of ground today. We've seen recursion, iteration with a dummy node, this awesome in-place iteration, even that approach where we created new nodes. So many ways to solve this merging problem.
And they all have their own strengths and weaknesses, depending on what you're trying to optimize for.
I hope our listeners are feeling inspired to tackle this challenge. It's a classic for a reason.
And remember, the best way to master these techniques is to try them out yourselves. Experiment.
Absolutely. Don't be afraid to try different approaches. See what works best for you. And as always, happy coding, everyone. Thanks for joining us on AI Code.